Microwave antennas, horn antennas, series on antennas and wave propagation, lecture number 5.10. Horn antennas are structures derived from waveguides, hollow pipe waveguides. When they are derived from rectangular waveguides, they are called rectangular horns, and when they are derived from a circular waveguide, then they are called conical horns. These horn antennas are prominent, widely used in microwave engineering. They exhibit a moderate amount of gain. In the present session, we focus on the study and understanding of horn antennas. Let us begin the session with a small introduction to this antenna. A horn consists of a flared length of waveguide ending in a radiating aperture. The other end connected to the feed guide is throat. So one side is aperture, another side is throat. Here it requires to be mentioned that these antennas, horn antennas, belong to the category of aperture antennas. These are used extensively as primary feeds. Primary feeds to lens antennas. Primary feeds to dish antennas. Since it has many electrical and mechanical advantages, it is easy to protect them from the weather by means of an electrically transparent radome. It can also be pressurized to avoid condensation. Mounting of antennas is most of the times in the outdoor environment. So they are prone to rain, they are prone to sun light, sun heat, they are prone to snow, they are prone to condensation. Unless proper precautions are taken, what happens is great amount of condensation can be there over the surface of the antenna. It increases the weight, it leads to a fall down to the ground because of increase of the weight, or it may be slightly displaced from the location where it is supposed to be there. It leads to some serious problems. So condensation or any other formation which disturbs the location of the antenna should be removed, eliminated, avoided. In case of horn antennas, it can be done with pressure. In addition, a large range of radiation characteristics such as polarization and propagation mode can be obtained with the different types of horns and excitation conditions. It means it is somewhat versatile. It is able to give different radiation characteristics, different types of polarizations, different varieties of propagation modes, of course with appropriate types of excitation conditions, appropriate types of horn structures. Some more points regarding these antennas. Indian radio researcher J.C. Bose is considered as using one of the first horn antennas constructed in 1897 in his pioneering experiments with microwaves. It is already mentioned these antennas belong to the category of microwaves. Microwave antennas. The first experimental research work on horns was conducted by Southworth and Barrow in 1936. The theoretical analysis of these antennas was performed in 1939 by barrow along with chew. The radar development during World War II further motivated the horn research, as they can be used as feed elements for radar antennas. Here it requires to be mentioned the fact that horn lens combination, it is a popular one widely used in the design of radars. Here is shown a horn antenna. This is a horn antenna. This is waveguide. It is opened out. Opened out in a vertical plane. It may be opened in a horizontal plane too. So this particular structure is derived from rectangular waveguide. That's why it is called rectangular horn. Input is fed here. Output comes out of the aperture. Field pattern is shown here. It's a beam. Here is throat. This is throat. So one end is throat, another end is aperture. This is surface, imaginary surface, which is bounded by the edges of the horn. This surface is aperture. If the horn is derived from a circular waveguide, this is circular waveguide. If it is derived from this waveguide, then it is called conical horn. Conical horn appears like aperture. Now is circular, throat also circular. This is called conical horn. There exist several types of horns like monomode, multi-mode, corrugated types. In each category, there are different forms depending upon the amount of aperture angle and the form of a transversal or longitudinal section. The type, direction, and amount of taper have a profound effect on the overall performance of the antenna. All these factors are taken into consideration to find the appropriate horn for the application on hand. Regarding functioning of horn antennas, here it can be explained in a simple way. Consider a waveguide, rectangular waveguide like this. When it is fed here on one side, the wave travels through the waveguide and comes out from the other end, moves into free space. But there is a problem. What is that problem? If you consider the opening through which the wave is entering into the space, up to this point, the wave sees one impedance of the waveguide, and while entering into the space, it sees another impedance of the space. These two impedances are different. Hence, what happens is a part of the wave gets reflected at this opening because of impedance mismatch. In fact, most of the wave gets reflected back towards the source. Hence, if we consider the gain of the wave that entered into the space, it is going to be very small. Wave itself is of small amplitude, gain also becomes, it's also small. So to increase the amplitude of the wave that enters into the space, moves towards the receiver, the technique used is flaring the walls of the waveguide, opening out of the walls of the guide. When it is opened, when walls are opened, then it results in waveguide, rectangular horn antenna. When horn antenna is in place, impedance mismatch gets reduced, more of the input wave enters into space, so its strength is more, so it is capable of moving large distances. It implies there can be huge distance between transmitter and receiver, an advantage. In addition, this advantage, reflections towards the source also gets reduced. It increases the efficiency of the system. Now let us move further to study more about horn antennas. Horn antennas basically are just opened out waveguides. All the horn antennas that are derived from rectangular waveguides are called rectangular horn antennas. The pyramidal and sectoral horns are examples for this category. So in rectangular horn antennas, two types are there. One pyramidal, another is sectoral. Pyramidal horn is a rectangular horn with flare in both the planes. They are a common type used with rectangular waveguides and radiate linearly polarized waves. Polarization is linear. So pyramidal horn is a rectangular horn in which the flare is in both the planes. Now sectoral horn. It is a rectangular horn flared out only in one direction. It can be viewed as a pyramidal horn with only one pair of sides flared and the other pair parallel. It produces a fan-shaped beam which is narrow in the plane of the flared sides but wide in the plane of narrow sides. These types are often used as feed horns for wide search radar antennas. E-plane sectoral horn is a rectangular horn flared in E-plane only. H-plane sectoral horn is one which is flared out only in H-plane. So what the points that are being told here are this. Antennas, horn antennas derived from rectangular waveguides. They are called rectangular horns. Horns are made by opening out of the walls. If walls are opened out in both the planes, then the horn is called pyramidal horn. Let us suppose this is waveguide, rectangular waveguide. Opening out of side walls like this can be done. Opening of broader walls also can be done. And both also can be done. Opening of side walls and broader walls too can be done. When opening is done in both the types of walls, then it is called pyramidal horn. If opening of only narrow walls, it is done, then the resultant horn is called H-plane horn. This is H-plane horn or H-plane sectoral horn. If opening is of only broader walls, these walls, then the resultant horn is called E-plane sectoral horn. Vertical plane parallel to narrow wall is E-plane. Horizontal plane parallel to broader wall is H-plane. So rectangular horns, pyramidal horns, sectoral horns, E-plane sectoral horn, H-plane sectoral horn, all these terms are explained here. Here is given a brief, complete brief about horn antennas. Horn antennas are opened out waveguides. Rectangular horns, conical horns. Rectangular horns are derived from rectangular waveguides. Conical horns are derived from circular waveguides. Two types of rectangular horns, pyramidal horns, sectoral horns. Pyramidal horns are opened out in two directions. Sectoral horns are opened out in only one direction. Sectoral horns are two types. E-plane horns opened out in vertical direction. H-plane horns, they are opened out in horizontal direction. Here are shown various types of rectangular horns. Sectoral H-plane horn. The narrow walls are opened out, pulled out like this. This is a H-plane. So opening out is in H-plane, that's why it is called H-plane horn. Sectoral H-plane horn. In C is shown sectoral E-plane. Broader walls are pulled out. Vertical plane parallel to side walls is E-plane. So here pulling out is in a vertical plane, E-plane. That's why this is called sectoral E-plane horn. In F is shown conical horn, circular waveguide. The wall is pulled out, resulting in conical horn. Now, in E is shown exponentially tapered conical horn. Here it is plain, but here it is tapered. Why it is tapered? What is the advantage we get? Main advantage is matching. Matching becomes smooth, eliminating reflections. Here you can see the wave sees a sudden discontinuity. Up to this, it is circular waveguide, and after that, it is a horn antenna whose cross-sectional area is increasing. So there is a discontinuity. Wave sees a discontinuity, it results in reflections. Mismatch gives rise to reflections. Reflections are always poisonous, harmful. So to avoid reflections, the structure is given a slow change. Similarly, in A also, you can find a pyramidal horn. In D, in B, in C, here the flaring is discontinuous. Here you can see this sudden flare. Flare starts suddenly, but here is gradual. As already mentioned, the purpose of this taper is to provide better matching, better continuity, so that reflections are prevented. Now, a few points regarding optimum horn. What is optimum horn? The gain of horn depends upon reflections internal to horn and flare angle. And for a given horn length, there is some flare angle that gives minimum reflection and maximum gain. Before going further, it requires to be explained what is a flare angle. This is a horn antenna, this is a waveguide. These walls which are opened out, they subtend certain angle somewhere here. This angle is called flare angle. If the opening is more and more, flare angle becomes more and more. One point requires to be mentioned here that the purpose of a flare, as already mentioned, is to increase the gain of the antenna. If a flare is not there, gain is almost nil. You don't find any gain from the simple waveguide. So flare is done, opening out is done to have more gain. When opening is more and more, flare angle also becomes more and more, gain also increases, becomes larger and larger. But this state of affairs continues up to a certain point. If a flare is further increased from this point, then gain starts falling down due to beam splitting. Before, what happens is this kind of pattern exists. When flare is made large, it is increased further and further. A point is reached where this single beam, it gets split into two beams like this. One beam, another beam. One harmful thing one can notice by comparing these two situations is that when beam split happens, gain falls down. This is unwanted. So point is, flare can be increased only up to certain point, or flare angle can be increased only to certain value. Beyond that, if you go, then what happens is we don't get any benefit. Instead, we get some harmful consequences. With this understanding, let us move. The internal reflections in horns happen at two locations, one lying at the aperture of the antenna and the other at the throat, where the sides begin to flare out. In the narrow horns with the small flare angles, the gain of the antenna is low because the small mouth approximates an open-ended waveguide, generating a large reflection. As the angle is increased, the reflection at the mouth decreases rapidly and the antenna's gain increases. In contrast, in wide horns, flare angles approaching 90 degrees, the gain is again low because the throat approximates an open-ended waveguide, generating maximum reflection. As the angle is decreased, the amount of reflection at this location drops and the gain again increases. Hence, it can be understood there is some flare angle between 0 and 90, which gives maximum gain and minimum reflection. So point is, when there is no flare, gain is minimum possible. When a flare is complete, maximum possible. In such case also, gain is negligible, minimum possible. In between, there exists a flare angle where gain is maximum. That angle lies in between 0 and 90 degrees. With the increase in flare angle, the aperture increases with a consequent increase in gain and synchronized decrease in the beam width. So till now our focus is on gain. With increase in flare angle, gain increases, but beam width decreases. This is an advantage. This trend continues only when delta is less than delta naught. Beyond delta naught, if the flare angle is further increased, beam splitting takes place. Hence, at delta equal to delta naught, the horn called optimum horn gives maximum gain and a minimum beam width for a given length. In this discussion, delta has come into being. What is delta? Consider horn antenna. This is a horn antenna. Let us suppose this is H-plane horn. This is H-plane horn. Now input is giving here. A part of the wave travels by the side walls like this. A part of the wave. Another part travels like this, straight, in a straight line, in the middle of the horn. By the time these two parts of the wave, this is one part which is traveling, touching the side walls. This is one part. Another part is traveling in the middle. These two parts, when they reach the aperture, must have traveled different distances because this distance is not same as this distance. So there comes into being a certain path difference between the part of the wave that is in the middle and part of the wave that is at the edges. That path difference is indicated by delta. It should not be too much. So there is a limit That limit is lambda naught. Delta is the path difference and the maximum allowed delta is delta naught. So with this understanding, now let us move further. A few points regarding optimum horn. Optimum horn is one which gives maximum gain and minimum beam width. Normally we want maximum gain from an antenna. We also expect minimum beam width from an antenna. So optimum horn is one which gives maximum gain and minimum beam width for a given length. The length of such an antenna can be found equal to delta naught cos theta by 2 by 1 minus cos theta by 2. Here A is aperture. This is aperture. L is horn length. Theta is flare angle. This is flare angle. Delta is path difference between end ray and central ray. This is already explained. This delta cannot assume any arbitrary value, large value. Certain limitation is there. Here is illustrated delta. That limitation value is delta naught. Actual value of delta naught depends upon the flare. If it is in E plane, one value. If it is in H plane, another value. Now, a few parameters, performance indicators of horn antennas. For optimum E plane horn, in E plane, the beam width is 56 by AE delta. This is half power beam width in degrees. AE. AE means A stands for aperture, E stands for E plane. So aperture in E plane in terms of lambda. For optimum H plane horn, in H plane the beam width is 67 by AH lambda. In degrees, it is a half power beam width. For non-optimum horn, in the planes in which field distribution is uniform, half wave beam width is 51 by L lambda. L is aperture. Lambda indicates that aperture in wavelengths. Now, directivity. Pyramidal horn directivity is given by 7.5 AP by lambda square. It is 10 log 7.5 AP by lambda square in decibels, dBi. It can be shown equal to 10 log 7.5 AE lambda AH lambda. The meaning of AE lambda AH lambda already explained. AP means physical area, physical aperture area. Physical aperture area multiplied by aperture efficiency gives effective aperture. So D is effective aperture by lambda square into 4 pi. From physical aperture, effective aperture can be obtained by multiplying physical aperture with aperture efficiency. Usually it is 0.6 or 0.7. Using that value, one can obtain expression for D. Physical aperture means physical area. That area can be found. Above is valid when path difference delta is less than its optimum value by delta naught. It is 0.25 to 0.4 lambda. Applications of these antennas. It is one of the most widely used antennas at microwave frequencies. The important applications include gain standard for calibration of other antennas, feed for reflectors and lenses, as pickup probe for sampling power, as an antenna in transmitters and receivers. A few advantages of these antennas are mentioned here. These antennas have several advantages when compared to their competitors in the microwave region. What are they? ease of excitation and versatility, good directivity, adequate bandwidth, simple mechanical construction, convenient to use with waveguides. These are advantages. A few points regarding performance. The horn antennas have no resonant elements and hence they can work over a wide range of frequencies. So these are broadband antennas. This results in a wide bandwidth, great advantage. Their usable bandwidth is typically 10 is to 1 and it can even be up to 20 to 1. These horns which operate 1 gigahertz to 20 gigahertz also exists. This is the typical frequency range of horn antennas. As already mentioned, horn antennas are popular in combination with the lens antennas. The input impedance is not constant but slowly varying over the frequency range, giving only inconsiderable mismatch and low VSWR over the bandwidth. Gain of horn antennas ranges from 10 to 20 dBi, in some cases even up to 25 dBi. A few points regarding special horns. Exponentially tapered horn. It is already shown in an earlier slide. The purpose of tapering is to reduce reflections. Septum horns are there. They are meant for reducing side lobe level. Corrugated horns are there. They are there to reduce cross polarization. Ridge horns are there for bandwidth enhancement. So these are considered as special horns, some special kind of design structure exists for these antennas. Here is the shown special horns. This is a tapered horn. This is a septum horn. This is a corrugated horn. This is a ridge horn. Ridge. Here is a ridge. With this, we come to an end to the present session. Horn antennas are introduced. Their functioning is described. Their structure is explained. Important performance indicators are given along with their merits, advantages, applications, and also special types. Hope this session is useful to you. We meet again in another session with a new topic soon.